Okay, YouTube, in the last couple of videos, we've expressed the desire to want to have a perfect square trinomial on one side of an equation when we're solving quadratics and a constant on the other, because if we have a perfect square trinomial, then we can rewrite it as some squared expression equaling some constant. I'll just call it d, and we could solve this just by taking the square root of both sides. So in the last video, we specifically focused on how we could rewrite the left-hand side as being a perfect square trinomial, and what we discovered was this: given some expression x squared plus bx, if we add on half of the middle term and square it, then we get not only a perfect square trinomial, but something that must factor into the square of a binomial, where what's going in here is just half of that middle term that we squared to get this value in the first place. So this very first equation right here, basically what I want to point out is that the left side is not currently a perfect square trinomial. I notice that -5 is not a perfect square of anything real that I can think of. So here's what I'm going to do. I'm going to outline how we'll treat this situation. And essentially, the first thing we'll always do is we will get this constant out of the way. So we're going to say move the loose constant over to the other side. That's going to be the first thing that I do when I complete the square. So now I'm left with an expression that says x squared minus 4x. And this looks very much like the x squared plus bx part of this perfect square trinomial. And then all we'll have is on the right side, we'll have a positive 5 now. What I want to do though is I'm going to add on now half of the middle term squared to both sides. So we're going to add to both sides the value b over 2 squared. Okay, so I notice here that half of my middle term is a -2, and if I take that -2 and square it, I actually get a positive 4. So you notice I said add to both sides. Well, the reason why is because this is an equation, and if it's an equation, then what that means, what you do on one side you have to do to the other. So now that I've added this 4 to both sides, what I want to do is congratulate us, because now we have what we call a perfect square trinomial, and not only that, it has to factor into the square of a binomial. So the left side, the whole point of doing this was to rewrite the left side so that it is the square of something, and in this case I say, well, what would I put in here? Recall that it's always half of the middle term. So in this case, half of our middle term here, or half of our b value, is -2, and on the right side we have a 9. So what's so wonderful about this? Well, what's so wonderful is the fact that I have something squared on the left equaling a constant on the right. So now we can solve this equation using square roots, where on the left now I just have x minus 2, and on the right I have the square root of 9, which simplifies out to being plus or minus 3. So now adding 2 to both sides of this equation, what we end up with now is something where we could say it follows that x is equal to positive 2 plus or minus 3, or in other words, we would say x is equal to positive 2 plus 3, which is 5, and positive 2 minus 3, which is -1 here in this particular instance, okay? And so what I want to do is, in these last couple of examples, have you give this a shot. So try to pause the video and really try to rewrite these as perfect square trinomials. As soon as you're done, you can go ahead and continue with me now. So essentially, we'll repeat the steps that we had up here. Move the loose constant to the other side. I suppose I need to supplement these steps a little bit here, but notice that we're really just trying to get this x squared plus bx phrase on the left. And then we'll say, okay, well, what I really want to add to this to make it a perfect square trinomial. So we say add to both sides the value of b halves squared. So half of our 18 in this case is 9, and 9 squared gives us a 49. Oh, 9 squared is not 49, it's 81. So we'd say adding 81 to both sides in this particular instance. That would make this left side a perfect square trinomial. So once we have added that b halves squared, we're going to factor into the square of a binomial. So on the left side here, we can see that this is going to factor into x, this thing squared, where we'll put in half of our middle term here, which in this case is a positive 9. And on the right side, I'll just go ahead and combine like terms, which is 91. So in this case, I'm going to take the square root of both sides, now that I have a squared expression on the left and a constant on the right, and I'll put plus or minus the square root of 91 over here. Now, I do not believe this is divisible by 3, nor by 2. I don't think it's divisible by 4, nor 5. And I can't see a 6 going into it if 3 is not going to work for us. So basically, I think 91 is prime. We can leave this radical as it is, and we'll subtract 9 from both sides of this equation now. So we would get x equals -9 plus or minus the square root of 91. So step 4, I suppose, would be this. Solve using square roots. Using square roots. And the whole point is to rewrite our trinomial into a perfect square trinomial so that we can factor it into a squared binomial and use square roots. So our two answers this time are negative 9 plus the square root of 91 and negative 9 minus the square root of 91. So this last example here, what I want everybody to see is step 1. Actually, this happens sometimes. Step 1's already been done for us. We have this loose constant on the right side. And the other thing I want everybody to notice is this. Our middle term happens to be odd in this case. And so I'm actually going to write this out very explicitly in this case. What we're adding in half of this negative 7, so negative 7 halves, and squaring it. And so in this case, I get on the left side x squared minus 7x plus 49 over 4, which on the right side we have to add in this negative 7 halves squared, which in this case is going to come out to be negative 1 plus 49 fourths. So we're going to need a common denominator on the right side, but the left side, I'll tell you what, this is our third step, it has to factor into the square of a binomial where what's in here, remember, is just half of our b term that we squared to get this value in the first place. So on the right side here I have negative 4 fourths plus 49 fourths gives us 45 total fourths. So I am going to take the square root of both sides here, which is really the square root of that fraction. And so we end up with this. X minus 7 over 2 just on its own is equal to now plus or minus the square root of 45 over the square root of 4. Remember, when you take the square root of a fraction, we can use our quotient rule to split this up. So I am going to clean this up quite a bit here. I would say that x minus 7 halves is certainly still on the left side. But on the right, I know that plus or minus the square root of 45 is really, this is a 9 times 5. And I only say 9 because 9 is a perfect square. And then also this, we would say the square root of 4 is just 2. So now we'll finish this off by adding the square root of halves to the right side. And I apologize because I'm a little out of room here. I suppose that, here we go. Ooh, I can scroll down. We will add 7 halves to both sides. And it's no biggie that we're dealing with fractions here. These cancel just like whole numbers would. But we would say that I'm left with x on the left, and we would get a positive 7 halves, plus or minus. Now, the square root of 9 up here we say would be a 3. So we say plus or minus 3 times the square root of 5 all over 2. And last but not least, because we have a common denominator, we'll go ahead and put everybody over 2, and we say that our two answers are 7 plus or minus 3 times the square root of 5. So these are the roots here that we found solving by completing the square. Cheers.